All right. Well, first of all, thank you for the introduction. So let's dive right in. So before I talk about any of the technical work, I do want to make a quick shout out to the team that worked on this particular aspect of Cadre, and also recognize all those people that weren't shown that made it possible, because certainly what we're going to talk about today requires things like flight software and avionics and all the things around it to even have been put into existence. But yeah, these three people here, including myself, worked on this particular aspect of Cadre. So more specifically, so Cadre is a technology demonstration that's going to the moon with 3 rovers and a base station. They all have the same avionics. It's a Snapdragon 821 with a quad-core CPU and a GPU, and that'll become obvious why I'm pointing out the GPU a little bit later. But basically, they're performing a multitude of multi-agent autonomous algorithms and functions. And some of these algorithms do solve rather large problems with various dimensions, but that means that they require quite a bit of compute time, and compute time is something that we want to minimize because we tend to be very time and thermal limited during our mission, which is only a single lunar day, and it also gets incredibly hot at the lunar equator. So today I'm going to talk a little bit about how we split up one specific expensive operation, which is this map merging operations, where you have multiple agents that are generating maps, and we want to merge that all into one cohesive map for planning. Like I mentioned, Cadre itself is a tech demonstration, so we're demonstrating this new technology on the moon next year. Actually, it's going to be part of a Eclipse mission, which is going to be flown by Intuitive Machines IM-3 mission. And as I mentioned before, we're headed to Reina Gamma, which is roughly the moon's equatorial region. And we're focusing on specifically on autonomy, but what I'm talking about today is really a function that supports autonomy, because for them to be able to do cooperative exploration and distributed measurements, they need to be able to plan together. And to be able to plan together, they need to have a unified understanding of what the environment looks like. So the key challenges, again, for software are a little bit more illustrated here, although I already mentioned them. But due to being at Reina Gamma and having quite a bit of compute on board, the robots do heat up quickly. So we have them on a 30-minute sleep-wake cycle so that they have opportunities to shut down and cool off, and then wake back up and then accumulate a thermal load until they hit the max, and then they go back to sleep, and they kind of do this over and over again. The sleeping also allows them to recharge their batteries. But again, the key takeaways really here are just try to keep your planning time short. I mean, you want to do a good job of planning, but you want to minimize the time, because if you spend too much of that cycle thinking, the robots are not going to have enough time doing anything productive, right? And then you have to replan come next cycle anyways. So I also mentioned that maps are important in the planning problem. That's because we've got behaviors that are typically solving some sort of motion planning problem or a path planning problem, where we have to decide where we want to send the robots or how we want to send the robots to a specific location. So on the left-hand side, I have kind of the diagram for one of those behaviors, which is the formation sensing or the distributed measurement one. But really, all you really need to take away is that, again, to be able to plan for the team, they need to have a unified vision or representation of the environment, and that's what we're trying to do here. And really, the way that we represent them in our system is these occupancy grid maps, which really are just these multi-state maps where for each cell or pixel in the environment, you're maintaining whether you've explored that before, or if you haven't, then it's unknown, or you have it be free space or it's occupied, right? So that way you can basically plan these collision-free paths for the robots in their environment. And in fact, if you're having any sort of deja vu from 2023, it's because I did give a talk about how we used OpenCL to speed up this particular algorithm, but we're focusing on OpenGL and a slightly different problem this year. So as I mentioned, each rover records a local multi-resolution traversability map. It's higher resolution close to the robot, and then as you get farther from the robot, the representation drops off in resolution to save on both memory and compute time. And they store a history of these maps on board and attach a state estimate to each of those locations. So for each representation of the local map, you also have a position and orientation of the robot and a timestamp of when that was taken. So you can imagine that the map merging problem is really what you want to do is you want to take all the history of maps from the robots, put them in one location, and then merge them according to some merge policy. And your merge policy could be driven by different priorities that you have. Maybe you trust everything that's in the high resolution more than you trust it in the lower resolution, or you always trust things to be occupied over free or unknown because you want to be extra careful. But the point is that you could have different merging policies or different combinations of merging policies that you want to implement and you want to apply so that the resulting merged map is kind of the best representation of the world that you have for the system that you can use for its planning. So here's a little bit more of a breakdown of how we think about our merge policy. We really have it in three different parts. So there's time. So typically you want to believe newer data more so than older data. Though it's not as huge as a factor because the environment is fairly static, but still generally we trust newer data over older data. Then we have a resolution. We want to trust higher resolution more than lower resolution data because it gives us a more finer definition of obstacles and makes the planner have to be less conservative, right? Like if you have lower resolution, that means you have to mark off large blocks in your map. So high resolution data is typically more desirable than lower resolution data. And then you also have the occupancy type. So typically we really want to avoid any sort of hazard and not drive the robots into the hazards. And so even if you have a false obstacle in your map, you're probably going to prioritize keeping that on the map over taking the chance that it's actually free. The expensive operations are as follows, but before I jump into really kind of the assumptions that you need to know about is that we have these occupancy grid maps and they're stored as these unsigned int8 arrays associated with the state estimate. So that's what you have. And then you also have maps of different resolutions. So they can vary in resolution. So those are two of the factors that you really need to, or maybe three of the factors that you need to consider. So the expensive problems that you need to solve are, first of all, if you're trying to merge two maps with different resolutions, you have to put them into the same resolution to be able to compare them cell by cell. They also have to be transformed properly, right? Because you're storing them just as a two-dimensional array with a little metadata thing that tells you the position and the orientation. But you actually need to project those properly into the world space. And then third, that each cell we want to merge the values according to your desired merge policy. So before I show you the solution to that, I want to point out I did mention it in the title that we're going to be using OpenGL. So it's another framework for writing code for the GPU specifically. You typically have input data in the form of like images or textures, and then you operate on output data, which is typically in OpenGL speak your frame buffer. And then the operations that you can apply to the textures and frame buffers and the geometries that you have are shaders. And the two shaders that are relevant to today talk are the vertex shader and the fragment shader. The vertex shader typically deals with the geometries, so mapping textures into rectangles, or you can think of it just basically transforming maps into the world space. And then you have the fragment shader, which operates on RGB values, or depending on how you configure OpenGL, it could be different kinds of color channels. But effectively, those are values at each pixel, which you can think of as a cell in the map. And the nice thing is that all of these operations, these shaders there can be many shaders on the GPU, so you can execute this in parallel very efficiently. And you can also, of course, allocate memory externally and make that accessible to the GPU. So the GPU reads in the textures, has access to the frame buffer, and it does all the operations on the memory that you've already allocated. So you don't have to worry about dynamic memory allocation, really. So the good news is that already spoiled early on that we have this really nice avionics package with a quad-core CPU, and it also has a GPU. So it has the Adreno 530 GPU. That GPU is in the chip, so it's not like a dedicated GPU. It's built into the chip itself. What we built is a library called GLAM, or OpenGL Accelerated Map Merging, which takes advantage of these OpenGL, specifically the ES shaders, which allow you to do the shader programming and offload the map merging operation of thousands of maps that we have to merge sometimes, right? The longer the robots have been exploring, the more maps they'll have generated. So the merging problem just keeps scaling larger and larger, and you end up with thousands of maps for your run. So the other piece of that was not just the OpenGL, but we also used EGL, which allows you to basically do this headless or off-screen rendering on an embedded platform, and that way you don't need an actual desktop or display output. You can do this just on the frame buffers directly. And then the only other note I wanted to mention is that even though we did all this work, it turned out that we weren't able to get the voxel drivers to run this in hardware mode on the voxel GPU. At the end of the day, we were able to do this on just about any other machine, but not on the voxel. But you can still run this in software emulation mode. And if you look at the right-hand side, even the software emulation mode was still faster than what we had implemented naively with dlib on the CPU. So you can see there's some really nice performance gains to be had, even as you increase the number of maps that you're merging significantly. So it's still worth it to do this, even if at the end of the day you have to use software rendering. So a little bit more specifically about the map merging operation. So again, we had time. So that's one thing that we didn't do on the GPU. We decided that to deal with our time priority, we would just pre-sort the maps according to time, because we already had all the maps in a database, so it was incredibly easy to just pull out all the map data ordered by time, because that was the key in the database. But after that, we then take full use of the GPU. Like I said, the vertex shader helps us with the transform, so it allows us to translate and rotate maps according to the associated state estimate that we get out of the database for that particular piece of the map. Then the way that we deal with resolution is that we load the occupancy grids, which is just the 2D array, and turn that into a texture. And we map that into basically into the texture part of the GPU pipeline at the highest resolution, right? So you take the highest resolution that you have as the base image. So even if you are if you're effectively, for low resolution maps, you're almost like super sampling it, right? So you're just repeating the cell multiple times into multiple pixels. And then the last point is the fragment shader, which is responsible for dealing with the occupancy type. So the fragment shader represents each cell. It goes over each cell and then merges it according to the value. So the value, you just build a rule based on the value. And we really only, since we have these, only really 3 states that they can be in, we only really need to use a single red channel to store that data. So it only uses the red channel to perform this operation. And that's really it. So when you put that all together, you really get this kind of algorithm where you sort the maps, and then you sequentially do your merge operation into a single off-screen frame buffer. Your vertex shader again computes screen coordinates from map properties, so your location, orientation, world size. That gives you the transform. So vertex shader very quickly just applies to the texture all the transforms, and basically as a rectangle that it then can put into the frame buffer. And then the fragment shader goes over the entire image, which will represent your merged map, which is that frame, or the larger frame buffer, and then just pixel by pixel applies the merge policy, and then you just iterate this until you're through with all of your maps, and then you have a merged map. So a little bit about the implementation. This was done. So this is we did a flight software implementation of this. So there's a component in F prime that has access to this library to perform this operation. It's all implemented in C++ 14. For some of the memory management stuff going in and out of this algorithm, we used ETL instead of the standard library to get statically allocated memory. And then this is built for ARM v8 64-bit with the standard platform optimizations. And there's also a link to a GitHub repo if you want to look at one of the early GLAM prototypes to kind of just see the basics of how those vertex and fragment shaders, for example, are implemented, and also how you can load from an image format into texture and all the necessarily building components that you would need to build this on your own. So in conclusion, what we saw is a speed up from using our specialized hardware. Once again, the same thing as we did with OpenGL last time. It's obvious that you get a speed up by using specialized hardware, but I think this is again exciting. Another aspect of finding a specific operation within an autonomous system that can be sped up by using a GPU or a multi-core CPU. And again, I think the implementation was fairly straightforward using OpenGL versus implementing our own thread-safe version. I think once we had cast this problem as something that the GPU could do, it became kind of obvious, like, oh yeah, of course you would just do this, and this is a really clean and simple way. Like really, the fragment shaders and vertex shader code is extremely simple. Even for the merge policy, it's just a bunch of if-else statements that it goes through to evaluate what the pixel should be in that location, and corresponding what the value should be in a particular cell in the map. And it has nice configurability, and it still satisfies all the typical things that we want out of flight software. And that's it.
Yeah, let's give him a round of applause. Some live questions? Come on.
Thank you for your presentation. Question on slide 13. In this picture, where was the primary bottleneck in terms of the computation?
So in general, for the problem, it's really a combination of all these three: the transform, resolution, and occupancy type, right? Because what you're trying to do is you've got two maps that are coming from two different robots that might, like, let's say that they overlap. So you have to be able to, what you really want to do is you want to merge, you want to apply a merging operation to two overlapping cells. So figuring out where that overlapping cell is in space is the computationally expensive part. So by using the GPU to transform these, let's ignore resolution for a second, and then having basically done all the work to make them overlap into a common grid or array, if you will, then you can just iterate over that array and apply your merging policy. That's really the expensive part of trying to do this not on the GPU. that this solves. So I don't know if there's like a particular, I don't think I have not run any profiling code on the GPU implementation to see where the bottleneck would be in this particular GPU implementation. But I think the point of the talk is that in the if you just implemented this as an algorithm on the CPU, just naively, that's what would be expensive, and the GPU implementation overcomes that limitation.
All right, we have a question online from here. Did you consider using OpenCL as opposed to OpenGL?
We asked for other things. Again, we had a talk 2 years ago about how we used OpenCL. So for this particular problem, I think we had a brief discussion about it, but it felt really natural to take care of to use OpenGL. I think primarily what drove this was the fact that we had multiple different resolution maps. And once we had thought of the fact that if you want to cast those all into the same resolution, doing texture mapping on the GPU was the right thing to do. And then I think that transforms and the merging operation kind of fell in place. Like, I think it was really the resolution part that drove us towards using OpenGL over OpenCL, because I think you'd have to manually implement that in OpenCL, whereas this is exactly what the GPU already does.
All right, thanks.
Yeah.
Other questions here?
Yeah, thank you for the talk. I'm curious if you can talk a little bit more about the ETL library and how you used it within F prime, and kind of what kind of, I guess, features and things the ETL library covers as far as the static memory allocation versus dynamic.
Yeah, absolutely. So I think this applies in general to all of the flight software that we wrote on Cadre. We wanted to have the ease of some of the data structures that you typically would get from the standard library, like vector, for example. But what you can do is in ETL, you can actually define a vector, but it looks like a standard array, in the sense that the ETL vector formulation will have like a template that's the type, which is what you expect, and then just like array, comma, like the size of it. So you can define a limit on the upper bound of the size of the vector, and ETL will take care of kind of static, basically allocating the memory for everything that you're going to do with the vector. And then you're getting rid of the kind of the dynamic growth, or maybe even shrinking of vectors that you might have, that somebody might do with standard library.
All right. Once again, let's thank Jean-Pierre.